So today we're going to basically finish topic 3. We were kind of really close at the end. I want to talk a little bit about test number 2, and we're going to start topic number 4. First, let's just talk a little bit about test number 2. Test number 2 is going to be next Monday. So you probably know what's going to be on test number 2. So test number 2 is basically is going to start at the Miller equivalence and move forward. So that's going to include water analysis, so hardness, alkalinity, those kind of things. And I actually have a question. I'll show you what a water analysis question is going to look like. And that's going to be basically half of the test is going to be a water analysis question. We talked about a few other things, or we will talk about a few other things, such as dissolved gases, colloids, organics, and some of the things we're going to talk about today. And the test will also cover a little bit of today's lecture, and I'll give you an idea of roughly where it's going to go to when we get there, but kind of some of the introductory material for topic 4. So that's next week. It's I guess it's going to be the same kind of format as last time. We're still not in person, and I think it seemed to work out okay last time. So I don't see any reason for changing the actual format. So that's what we will do. And if you have any questions, let me know. I will probably talk a little bit more about the test on Wednesday as well. Okay, so back to topic 3. If you take a look at this, we talked about all of these things now. We've talked about ions and expressing concentrations. We talked about water hardness, acidity and alkalinity, and all of these things here included the Miller equivalence. So Miller equivalence. So that will be a big part of the test. Last day we also talked a little bit about various dissolved gases, such as dissolved oxygen and some of the other important dissolved gases. We talked a little bit about colloids being kind of indissolvable things, and they're large enough to make water turbid. We talked a little bit about organic compounds, so that includes things like pesticides or medications that people take, and also any kind of debris that would come from living organisms, so plants, and could include fecal matter from farms or human waste and those kind of things. And we'll come back to waste and wastewater at some point later on in the semester. So I just wanted to kind of, we have this last little part, other water quality parameters. And some of these things that fall into this other category are going to be covered in a lot of detail in other things. So I'm just going to kind of touch on them now, and they're going to be important for a little bit for lab 3. So if you think about water quality in terms of things you can measure, this is a bunch of things that we talked about, chemical characteristics. So this includes, the big one, of course, is dissolved ions. And those dissolved ions may affect things like pH, hardness, alkalinity, and acidity. And they may not, right? They just may make something salty. If you have potassium, it doesn't affect the acidity or the hardness or anything like that. And total carbon and those kind of things, which is something we're going to kind of talk about a little bit later on when we get to wastewater and whatnot. You can also think of physical properties as well. And these would include things like turbidity, total dissolved solids. Again, like I said, we're going to come back to these things in later units, odors, temperature, color, those kind of things. And sometimes radioactivity is considered, not always measured unless you actually suspect there is a radioactivity issue. So a bunch of these things we're going to talk about, as we get to water treatment and wastewater and all that. So we will come back to a lot of these concepts. One thing I do want to talk about just for a few minutes, though, which is going to come up later, is this concept of total dissolved solids. So what do we mean by that? Just exactly that, everything that's dissolved in the water. And in most cases, this includes mostly ions. And all of the ions we've been talking about, you can see there's a list there, right? Sodium chloride, sulfates, calcium, so on. It could include non-ionic things, right? So there are compounds out there, for example, let's say glucose. Glucose is a molecule that could be secreted from an organism or a cell, and it's not ionic, right? So it would fall into this category, although most of this is going to be ions. So these things are going to contribute to a few chemical characteristics, things that we've talked about already. For example, hardness, right? And that would include things like any calcium and magnesium. And if there's carbonate in there, that's going to contribute to alkalinity, those kind of things. They can also all contribute to taste as well. Certain ions, for example, are associated with a salty taste. And so sometimes we talk about total dissolved solids being related to saltiness. And I think I have a nice little graphic here that shows some of the different bottled waters. And so if you take a look at this, I know it's a little hard to read on some of them, but there's Dasani right in the middle. Dasani, I think, is produced by, I can't remember if it's Coca-Cola or Pepsi, but it's a pretty standard kind of bottled water. And you can see it's falling into what this author thinks is the good or excellent category in terms of its being a good pH and a good amount of total dissolved solids. So there's kind of a bar, is that if your total dissolved solids, if it's greater than 500 milligrams per liter, then it equals salty. Right, and so that's kind of the thing, right? With drinking water is we don't want things to be salty. But if we have not enough, then you're going to fall into this category, right? It's going to be bland. And some of that is kind of a preference, right? But generally, most people start to detect it as salty in that 500 milligrams per liter range. So you can see there's a few up here. Perrier, for example, is a pretty famous bottled water. And I can't remember the exact value, but according to this chart, it's probably around 600. And it's quite flavorful if you ever have Perrier. And I actually kind of like it, but some people do find it kind of salty. I haven't had this one here, but Bedoit. I haven't had that one, but anyway, again, a matter of preference kind of thing. But generally with drinking water, we are aiming for less than 500 milligrams per liter, but not too little because we don't want it to be bland either. Total dissolved solids is often also a measure of pollution, right? So if you think of all the possible contributors to pollution that include agricultural sources, right? We could talk about feces or fertilizers, those kind of things. In Canada, we salt the roads. We add, depending on where you are in Canada, there's lots of road salt added, those kind of things. But can include all sorts of other industries and whatnot. And so sometimes it's looked at as not just necessarily something to do with taste for drinking water, but as also a measure of how polluted the water is. And there could be health effects for having these kind of things. We don't want things to be, extra salty, because that can actually be hard on your kidneys and other parts of your body, those kind of things. And of course, waters that have lots of total dissolved solids can have effects on machinery and all sorts of other issues. So again, think of it as two things, right? One is a taste health kind of thing, and two is sort of a measure of pollution in some cases, right? Again, it doesn't matter necessarily what's in it. What is in it may give it specific properties, make it more toxic or less toxic, or taste, weirder, or if you have lots of iron or copper in something, they have a particular taste, right? So it's a little bit of a different thing. So the last thing, kind of just to connect this to what's coming up in this week's lab, is this week's lab we are going to measure conductivity as one of the exercises we're doing. And this is, I'm not sure if this is the conductivity meter we're going to use. We have a few different ones, but that's one of the ones we have in the lab. And this conductivity meter can actually measure conductivity and pH. And we're going to calibrate it, and we're going to measure conductivity. So what is conductivity? Conductivity is measuring the amount of electricity that can flow through a sample. So generally, conductivity is directly related to total dissolved solids because most of those total dissolved solids are ions. So there's generally kind of a very correlational relationship. And so conductivity you measure, it's very quick, use the probe, and then it automatically gives you an idea of what the total dissolved solids is. Later on in the semester, lab 6 or 7, we're going to measure total dissolved solids the traditional way, and you're going to see it takes time, right? Whereas using a meter is very, very quickly. So this is measured in units of Siemens per centimeter. I don't really understand conductivity in terms of the physics of that, but it's going to be micro or millisiemens. So make sure when you're reading the meter, you are taking a look to see is it reading micro or reading milli, just so that you get the units correct on that. So that's kind of it for topic 3. Like I said, I have a water analysis question that I want to show you. And so for lab 3, we're going to do a bunch of water analysis. We're going to measure a bunch of these ions. We're going to measure conductivity, pH of a bunch of water samples. And so lab 3 is a pretty important lab for this course. All right, so what I wanted to do was show everyone kind of a water analysis question, and something like this is going to end up on the test, right? And like I said, this is going to be, maybe 10 out of the 20 marks. So you should probably be comfortable with answering this kind of question. I may ask you all of these things, or I may ask you some of these things. Like I said, my goal is to kind of get 10 marks out of it. And, depending on where I need some more marks, I could make it worth 9 marks or 12 marks or something like that, depending on the actual test. But here's an idea of what it's going to look like. You're going to have a water analysis that's been performed, or at least measured the concentration of some different ions in a water sample. And typically those concentrations are given in milligrams per liter. You are also going to be given the equivalent weight of some of these things, and then asked a bunch of questions about it, right? So let's take a look at these one by one. So first question, it says, for each of the dissolved ions, convert milligrams per liter to milliequivalent per liter. So remember the equation, okay? The equation is we convert, so milliequivalents per liter is equal to the milligrams per liter divided by the equivalent weight. So as I was showing you before in class, what you can do is just think about there being a divided sign right here. So 185 divided by 20 is 9.25, and so on. And so fill it in. Please show a sample calculation so I can give you the part marks. If you do make an error, I can at least give you part marks if you get part of the question right. So that's the first part. That's really the first part of all this analysis, is to convert everything to milliequivalents per liter, because we need those values for many of the other questions. That's part 1. Part B, it says draw a milliequivalents per liter bar graph. Okay, so if everyone does this right on the test, I will never ask you to do this again. I showed you how to do this before. Remember, you want to have a scale, and I recommend that you use 1 centimeter equals 1 milliequivalent per liter. And then you're going to basically draw these out. So you draw a bar for each ion. So there's calcium, for example. We can add in magnesium, and notice that in this case here, what I've done is I've added 9.25 plus the value for magnesium, which is 3.93. And that's where that value there comes in. And we have sodium. Usually these are done in the order of large to small. So the largest would be the first one done, and then you get smaller and smaller. And then we have our anions, so we can draw that one in. There's the bicarbonate, the sulfate, the carbonate, and the chloride. And so notice that these don't add up, right? Our anions and our cations do not add up. So I think, is that the next question? I can't remember. Not quite. But that would be a good question, right? Why do these things not add up? And if you don't remember the answer to that, you may have to go back and look at your notes from the previous lecture. But there are several reasons why they may not add up, and I'm not going to go over that now. So list all hypothetical combinations, right? I'm not going to ask you for every single hypothetical combination, but in this case, you can see I'm asking for sulfate. So remember for sulfate, so here's sulfate right here. So what I'm doing is just combining all sulfate with each of the cations, right? So you can have calcium sulfate. So notice in this case here, I'm not asking for molecular formula or the name. So I'm just giving the molecular formula, but you could give either, or I could ask you for the molecular formulas, or I could ask you just for the names. So maybe I will put both here. So we have calcium sulfate. This is supposed to be a comma. It's not a very good comma, is it? Okay, what else? We have magnesium sulfate. Okay, magnesium. Sulfate, and then we have one more cation. So we have sodium sulfate. So remember to get your chemical compound correct, because sulfate is has a valence of 2 negative, and so we have to combine 2 sodiums. So that's sodium sulfate. Okay, so this is the whole idea behind the hypothetical combinations, is what minerals are going to form when this water dries up, right? And that's kind of important to think about these things. All right, what would be D? D is calculate the balance error. Okay, so you got to remember the equation for that one. And so this is the equation for balance error. And so it's basically the sum of the cations. So the cations was what, 15.4, something like that, minus the sum of the anions divided by the sum of all of them times 100. And so in this case here, there's the values 15.4 minus 13.51 divided by the sum of all that times 100. And so the value is 6.57. And depending on what you're looking at, that's not amazing. A lot of things that I have read have said that less than 10% is decent. I think it really just depends on what you're trying to do here. So why are they not equal? I think we mentioned in class before, there are quite a few reasons why that might be. One is there's error in the measurement mechanisms, right? In all of the test kits or whatever is being used, there's always a little bit of error. And so then the numbers aren't going to be exact. Sometimes you're not measuring everything. Maybe this sample has a lot of iron in it, and that's what's missing from the cations. There's a lot of reasons for that. Sometimes some ions are affected by the handling process. Carbonate and bicarbonate sometimes can be lost if the pH is a certain temperature, pH is a certain value, and those kind of things. But those are some of the main reasons anyway. Okay, so of course we're going to be asked to calculate hardness and alkalinity. Okay, so remember, for hardness, what do we need to do? We need to add up all of the divalent cations, which usually means calcium and magnesium. So the first step was convert these values to milliequivalent per liter. We've already done that. The second step is to add them up, and that would give me the total amount of hardness. So in this case, 9.25 plus 3.93. And then the third step is we convert that value. So this is the amount of hardness, and we want to convert that to milligrams per liter calcium carbonate. And so we just multiply that by the equivalent weight of calcium carbonate, which is given here. That's why it's on the table. And the value is 50. You multiply that by 13.3, and this is the answer you get. So that's actually really hard water. And that might be another question I might ask, right? Is this hard, right? And if that's the case, I'd give you a table to, you know, kind of maybe help with the discussion or something like that. All right, that's E. And F is calculate the alkalinity. By the way, if I'm going too fast or too slow, please always let me know, okay? At this point, we've done this a few times already, and I'm probably going a little fast and hoping that everyone has an idea of how to do this. Do encourage you to look at the problems and do them, work them out on your own. I have a second problem set that I've added with this unit that goes into these water analysis questions, and there's lots of practice problems there for you. So alkalinity, remember alkalinity is bicarbonate and carbonate. So the first step is, of course, convert everything to milliequivalents per liter, which has already been done. Second step is basically add up the amount of alkalinity. So we're adding up the milliequivalents per liter of bicarbonate and carbonate. So that is 9.39 milliequivalents per liter. And then the last step is the same as what we did with hardness. You are multiplying it by the equivalent weight of calcium carbonate, which is 50. And so we're getting 469. So notice that alkalinity and hardness are not the same. Of course, they're not the same. They are due to the water, to the properties of different ions. Sometimes they're similar. If all of the hardness was from calcium carbonate, then it would be the same value. Okay, so I think that is it for water chemistry. So if you can survive test number 2, then you probably have no problem surviving the rest of the course. This is where all the most complex mathematics is found in the course. Not that we are not going to do some more math, and not that we won't talk a little bit about chemistry here and there, but this is kind of the meatiest topic you're going to see in the whole course. So a lot of the rest of the course is a little bit easier, although we will continue to see various types of calculations. All right, so we're going to move on. So let's talk about water biology. Topic 4. By the way, I found this photo and I just thought it was really cool. And when you look up aquatic life, usually people are showing some sort of marine, you know, fancy clownfish and things like that. But I was looking for something that represented aquatic life in this part of the world. And there is a jackfish, also known as a northern pike. And it's in a freshwater ecosystem. I thought it was just a wonderful, wonderful photograph. And this was taken a few years ago in some sort of photography contest. But I thought that was just very, very cool, kind of up close and personal. So what are we talking about in terms of the biology part of water? We're talking about all the organisms that are going to be in there, right? And they're all doing things, right? They're living. And this is a video, by the way. I'm going to go see if I can play that. It's not playing for me. And there are quite a variety of things, right? You know, I know most people are used to thinking of plants and animals. We're not really going to talk a lot about plants and animals in this particular unit. What I want to do is focus a lot on organisms that are affecting water quality. Plants and animals can, of course, right? Animals, you know, they poop and they pee. Plants can die and decay and causing, you know, all sorts of organic matter that way. But we're more or less focusing on these other things with the star. So you can see bacteria, protozoa, viruses, and algae. There are fungi, there are worms and crustaceans, and we could really go crazy if we wanted to, but we're not going to focus in on everything here. So let's talk a little bit about some of these things. You can see some of the focus of this unit. We're going to talk a little bit about waterborne diseases, and then a little bit more about how some of these things can affect the water in terms of undesirable taste and things like that. We're going to talk about biochemical oxygen demand. So we did talk about that in the lab last week, and I will come back to it on Wednesday as a refresher and maybe give you a little bit more detail on that so that we're ready to complete lab 2 on Thursday. And very briefly, we'll talk about wastewater treatment, which is kind of all of topic 10. So we're not going to really get into that a lot here, but just kind of give you an idea of what the biology part of wastewater treatment is all about. Oh, what happened here? Somehow I have some wrong units, or some of the wrong slides in here. I want to talk about waterborne diseases. Okay, let's talk about waterborne diseases. Waterborne diseases are caused by a variety of organisms, and we're going to get into some of kind of the main ones. There's a whole bunch, a big list. They're very serious, and some of them, if you take a look, I've got a slide coming up, are a huge part of the disease burden of the world. And this is where we're very lucky in Canada, because we have very good water treatment and very high standards in most parts of the country. What was this I was going to say? So first of all, where do these things come from? And generally, this is the answer here, right? Waterborne diseases are mostly from fecal matter. And if you think about fecal matter, I guess I didn't leave myself a lot of space, but there's actually three sources. So one is, of course, humans. And you can see that's what's shown here in this slide. We have human waste, okay? And that can obviously, if there's pathogens in the human waste and they get into your drinking water, then that is a big problem. But there's two other kind of sources, and I sort of have them broken up because they are sort of different. One is agriculture. So that's animals, of course. We're talking about manure and basically animal waste. Kind of the third category, which is usually considered a separate thing, is wildlife. And wildlife, of course, also has fecal matter that can be spread into things. In most cases, number one and number two are kind of the big deal, right? Because of the quantity and the proximity to humans. Wildlife in many cases is not a big deal. In some cases it is, which is sort of why it's actually a separate category. So just a few numbers for you. There are a lot of people who get sick every year from waterborne illnesses. The good news is that most are not life-threatening. You can see 90,000 cases or so, probably more. There's many that are not documented. My guess is that the real number is probably, a quarter to 500,000, quite honestly. And I'll probably get into that a bit more next week as to why I think those numbers are that high. But like I said, many aren't reported. And the good news is many are not life-threatening. So apparently about 90 deaths a year, according to, this is from the Canadian government stats that I found. But if you look at kind of worldwide, this is a big deal, right? 4% of all diseases. Actually, I got to double check that number because I'm pretty sure the number is much higher than that. And I'll show you why that is in a moment. And sometimes there are outbreaks that are quite serious, right? One of the more famous ones happened in Canada, happened in the year 2000 in Walkerton, Ontario. And this was highly publicized, and we'll talk a little bit about what happened in Walkerton, but quite a few people got ill, 2,500 people. I think this is a town of less than 10,000. So this is like, quarter to half of the town folk got ill from this, and a few people died, unfortunately. So this is why I think the burden is actually higher than 1.8 million. Like I said, I'll have to maybe double check some of my numbers. But if you take a look at this, this is the 6 leading infectious disease killers, right? And you can see that number 3 is diarrheal diseases. You're probably thinking, whoa, who's dying from diarrhea? Mostly we're talking about kids under 5 in developing countries, right? And in these countries, many countries do not have good sources of clean, sanitized water like we do in Canada. And so kids are dying from dehydration because they're getting diarrhea constantly, sometimes due to a variety of different pathogens. And like I said, this is a big deal in many parts of the world, and not for the most part a big deal in Canada because we do have very good water treatment systems. And like I said, we'll talk about water treatment a lot, but this is something I think a lot about, is infectious diseases and microorganisms. So I thought I'd show you this this number, some of these numbers here. Sometimes we see them in the news, and I want to just show you a few news items here. El Nino increases diarrheal disease apparently quite a bit. Some of you, I don't know, I guess you guys aren't that old, but some of you may remember Hurricane Katrina. And that was a big deal in New Orleans, and there was a whole bunch of waterborne diseases. After that public health failure, there was an earthquake in Haiti that led to a cholera epidemic, and so on. Maybe I should find some newer sources, since people are getting younger in my classes, it seems. Okay, so a few things about waterborne diseases before we get into some of the details. First of all, how can these things be controlled? Number one, of course, is just having water treatment, right? And this is what we do have in Canada. We have water treatment, and that is a big deal. It really is a very big deal. Something that came out 150 years ago and has led to massive improvements in public health is basically water treatment. Also treatment of wastewater. Okay, so that hopefully makes a lot of sense. We're not just treating our drinking water, but we're treating our wastewater before we dump it back into the river and pollute for all the people downstream. It's very important to treat our wastewater as well, of course. We can also protect our water sources, and maybe we'll touch a little bit on that in other units. But what does that mean? It means that we don't allow people to pollute our water sources. In some cases, it means we're not allowing, farms to be right next to the river. There's lots of ways we can protect our water sources, but mainly trying to prevent some various types of pollution. Sometimes we're looking at public health measures such as immunizations, and we'll touch on a couple of those things as we look at some of the different diseases where immunization is actually possible. So for example, if you work at the wastewater treatment plant, there's a few shots you may have to get that most normal people don't have to get to protect you from disease. Okay, just looking at where we are here. And one other thing I was going to say, let me just take a look here. Okay, yeah, I'm not quite at the point where I want to cut off for test 4, but there's a few other things I want to talk about. So let's talk about some of the organisms that are responsible for some of these diseases. And I want to talk a little bit about bacteria today, and a little bit about E. coli. E. coli may be one of the most famous of the bacteria. And then eventually we're going to talk about the protozoas and the viruses and the algae and the helminths. And so hopefully you know what some of these things are from Biology 108, and I'll kind of review what some of them are here now. So first is bacteria. So bacteria probably know are prokaryotes, right? So a prokaryote has no nucleus, and there's a lot that could be said about them in terms of their biology, and I talk about their cell walls, there's gram-negatives, gram-positives, those kind of things. But the first thing to know is they're prokaryotes, and they're single-celled, and they're very, very tiny. And the second thing to know is they're not plants. A lot of people seem to think bacteria are small plants. And I think this is just old information, and old by old, I mean like 200 years old, where people used to think they were plants. There was one water quality textbook I was reviewing for this class, and I basically threw it out because I got to the chapter on bacteria, and it talked about them being plants. And I'm like, this is just garbage. This person doesn't know what they're talking about. There were other issues with the textbook as well, but so just know they're not plants, they are prokaryotes. They are their own thing. They come in many shapes and sizes. There's a whole variety of them. You can see I have 3 listed here that are important for water quality. E. coli is important as an indicator of bacterial quality, and some E. colis can cause disease as well. But notice this other comment I have down here, is that bacteria are actually really important for wastewater treatment as well. So they're not all bad. A lot of people like to think of, okay, bacteria or germs, they're bad. Well, that's not true. And I could certainly go into that a lot, but we're mostly going to focus on these ones here. So let's talk a little bit about E. coli. And I think what I'm going to do, maybe what I'm going to do is cut off, I'm going to cut off where the test is here. Okay, I'm thinking that most of the test is going to be on the chemistry, maybe a little bit on these waterborne diseases. And maybe the other thing I'll say about these waterborne diseases is that the typical symptoms, and you're going to see this as a theme, are diarrhea and vomiting. So lots of fun there. So right there, that's where the test is cut off, okay? E. coli and everything forward is going to be on, that'll be way on test number 3, I guess. But I'm thinking that that's probably the place that I wanted to stop. So let's talk about E. coli a bit here, okay? So there's E. coli. E. coli is a gram-negative rod-shaped organism. You can see there's some photographs of it. It has flagella for swimming around. And it is found in your intestine. So if you are a warm-blooded animal, so if you're a mammal or a bird, you have E. coli. And so E. coli is not bad. That's why I have this little mostly harmless sort of clause. E. coli is doing us some wonderful things. It's living in our gut. It's making vitamin K for us, and it's making folic acid, and it's preventing some pathogens from colonizing our intestinal tract. And it's a great mutualistic relationship because, you know, we're feeding E. coli, we're giving it a warm, moist environment to live, but mostly harmless. So there's a hint there that sometimes it's harmless. And so this is kind of what I want to talk about here for a minute, is that when you look at the biology of E. coli, it's not just one thing, unfortunately. And this is where it gets kind of complex. So there's all sorts of strains out there that we would call non-pathogenic. So they're benign or commensals. They live in our guts or they live in laboratories. They're not making us sick at all. You can see there's some of the different strains out there that you might encounter, and often they have sort of funny names to them, and you don't need to know what those names are. Some of them fall into the purely pathogenic category, and these are the ones we're really worried about. You can see they have some different names as well, and I'll kind of define some of those names in a few minutes here. And these are the ones that you hear about in the news, right? So maybe I'll even write that down. We'll say news. So if you Google E. coli and you click that little news tab in Google, it's all about the bad ones. But those are not the ones that most people have in their guts. So like I said, this is where the confusion is. And these are the ones that are causing disease. And we'll talk about what some of those things are in a minute. And there's actually kind of a third category of E. coli, some that are potentially pathogenic. So these ones here, you know, are really just, they're benign, right? So we'll say they're benign, which means they're not going to hurt you. I guess I added an extra letter to benign, didn't I? Unless in the wrong place. So these are the ones that sometimes cause urinary tract infections, or there's cases where people get E. coli in the blood from, you know, from a wound or something like that. And so these ones here are kind of like, you know, we would call these an opportunistic infections in that they're normally okay, but then sometimes they're not. So it's kind of true with a lot of microorganisms. You know, you get them into the wrong place, and that's not a good thing. In the right place, it's not a problem. So I kind of want to just talk about some of these here in general. I think I have some slides on some of these. So you may notice that the pathogenic ones all have code names, like we have E-tech and E-pec and E-hec. So I'm not going to ask you to define those on the test, okay? They all stand for something to do with how the biology of that organism works. So the EC on the end of everything is E. coli. You can see the ET stands for enterotoxigenic, and it's kind of like they're being classified in terms of what kind of toxins and things like that they have. And I have some slides on each of these, but you can see I have in red the common theme here. Spread by human feces, spread by human feces. This one is spread by animal feces. This one is spread by human feces. So that's kind of one of the main points here, is that it's spread by fecal matter. So if you have clean water, not a concern. Sometimes, of course, the fecal matter can end up on food. And that's why we do end up with sometimes spinach recalls or romaine lettuce recalls and things like that. I have I think I have a slide for each of these, so it's worth it to kind of talk about these just a little bit. And like I said, there's just sort of some key points for some of these. So this is the one that, one of the ones that people hear about a lot is this E-tech. So you can see the E-tech is often the cause of travelers' diarrhea. So if you've ever gone on vacation or traveled to another country and you've had diarrhea that lasts for a day or two after eating some food or drinking some water, this is probably it. If you take a look, this is kind of a map of where the higher risk areas are, and of course many of them are tropical, warmer locations and favorite places for people to go and travel to. And this is kind of the thing, right? And so if you travel to Mexico, for example, one of the first things they tell you when you get off the plane is don't drink the water. It's going to make you sick. And that's true in a lot of places in Mexico. So the water treatment there is not at a standard that we have in Canada. If you're local, you can build up an immunity to this, but usually it takes a couple of years, unfortunately. So you're not going to build up immunity over if you're just there for a week or two for holidays. So this is the one, like I said, that is the one that many people have experienced. No fun, but it usually lasts a couple of days, kind of max. And that's usually the end of it for most people. So passed in human feces, right? So like I said, humans are a big problem sometimes. Here's another one, E-tech. This is the one that's more associated with diarrhea in infants and is killing babies in other countries. So by the way, a word to the wise. If you are on the internet and you are looking up something in Google Images, think about what you are searching for. In this case, I was searching for E-tech diarrhea, and let me just say I had some graphic photos. This one here I thought was a little nicer to show you. But unless you want to find pictures like that, but let's not get into that. But notice the theme here: passed in human feces, right? So this is the problem, right? If you don't have water sanitation. Now I do want to talk about EHEC. EHEC is enterohemorrhagic. So hemorrhagic, this word here often means bleeding. And this is the one that I want you to know a little bit about. So this is the usual strain here. E. Coli 0157 is the big strain that we hear about in the news. And this is where we often get recalls. So you can see there's somebody making fun of some spinach, a spinach recall. There was a big romaine lettuce recall about 2 years ago. I remember there was a sprouts recall. I remember seeing, what was the other one I remember seeing? And there's been also cases of this associated with certain restaurants. There was an outbreak many years ago in McDonald's with this particular organism. And notice it says, this one comes from animals. So you're probably wondering which animal. Well, where is it? Where is it? This animal here, cows. So it turns out that we have a lot of cows on this planet, and those cows can carry this organism and they don't get sick. So this is the problem, right? We have cows, we like cows, they give us milk, they give us hamburgers, and they're carrying an organism that could be very, very bad for us. And so we have to be careful when we slaughter the cows. We have to be careful in terms of, these recalls that we have. Often the case is what has happened is you have a farm that has a bunch of cows on it. And sometimes there's a lot of rain and floods and the manure spreads over into the spinach farm or the lettuce farm. And so you have all this food that gets contaminated. And that's often what happens in many cases with this kind of thing. And so, we have to monitor these things a little bit better in some cases, and it's unfortunate. I was just going to talk a little bit about Walkerton here. Notice there's a sign here. It says there's a risk of E. coli 157 infection. So this is an area you can see they're talking about some animals and stuff, and it must have been detected in the area. So this is what happened in Walkerton, Ontario, by the way. This was, I guess, 20-something years ago now. I remember it because I was living in Ontario at the time. and it was in the news like crazy. And so what happened here? This was a small town and they had a reservoir of water and there was some flooding. So some agricultural land flooded into the town reservoir. And you know what? This was a case where the people at the water treatment plant were ignoring, they were literally ignoring and denying that there was contamination. And there was a massive investigation of this. 7 people died, and some of those water treatment plant people they served time in jail for this. So it was very, very serious. And this actually changed water treatment standards in Canada in terms of what kind of qualifications you need to be as a water treatment technician, all those kind of things. So this was like I said, a pretty big deal at the time. And you do hear about these outbreaks once in a while. And usually when you see E. coli in the news, remember it's not just E. coli, but it's E. coli 0157 is the big one. And it's all because we like cows. Not every cow, of course. Notice it's about 28%. There's some studies that show as high as 50%, but that's not always the case. So notice this was a lot of diarrhea from E. coli, and in the case of the EHEC, we're talking about bloody diarrhea. So a lot of diarrhea here, and with diarrhea comes a lot of other, intestinal kind of digestive discomfort. So it can lead to diarrhea, cramps, those kind of things as well. So there are a bunch of other bacteria that are worth talking about, and I think what I want to do is I'm going to address the first 2 today. Shigella, I think I have a little slide here on Shigella and Salmonella. This will be my last slide for the day. So Shigella, by the way, is closely related to E. coli 0157. This is from human feces, though, rather than animal feces. So this comes up sometimes as an infection. In fact, this used to be one of these organisms that people used to classify as E. coli, and then at some point they decided it was different enough. Again, classification of biological organisms is always a debate, right? And so maybe some of those other strains of E. coli will someday be named something else, who knows? But not much really to say about that. Just again, you have a situation where human feces is contaminating a water source. Salmonella is related to E. coli as well. And Salmonella is often associated with what we would call food poisoning as well. And poisoning. And this is where we have fecal matter contaminating some food or water. Salmonella, by the way, is found in birds and reptiles. Reptiles, I can't spell today. And so it's often associated with chicken, right? Because chickens, they poop and their feces can get into meat or they can get on eggs. And this can lead to food poisoning, but it can contaminate water as well. And so you're looking at, again, we could have cramps, diarrhea, vomiting, and in many cases, people have fever with salmonella. Notice I said reptiles. So kind of one of the last points I want to make today is if you have a pet reptile, or if your friend has a pet reptile, let's say a snake or a turtle or something like that, and you're handling the pet turtle, wash your hands afterwards, because that snake or turtle is going to have salmonella, and you probably are going to get it on your hands after handling that pet. It's always a good idea to wash your hands when dealing with these things. All right, so that is, as promised, where I'm going to finish today. We do have a number of organisms that I do want to talk about, and you're going to see, like I said, there's common themes here. Contamination from feces, diarrhea, vomiting, these are all the common themes around these waterborne diseases. And most of them kind of have little points to take out. Like I said, E. coli, the big one is the 0157, is sort of a special case from animal feces. And we're going to come back and talk a little bit about E. coli later as well.